Hi, and welcome to this final video in this series of kinetics clips for both AS and A2. We're going to look at the final one here at the rate determining step and how we have derived the information of the rate determining step for a reaction. If we were to pick a random rate equation and suggest that it is equal to the rate constant multiplied by the concentration of A, that is telling us that, as we know, the reaction is first order with respect to A, and subsequently the variation of A's concentration will change the rate of its reaction. If the reaction we know is A plus D going to C plus E, a made-up reaction, we don't necessarily know how A plus D react. We don't know in what order subsequent steps happen. But if we were to do some theory and work out that what we believe happens is A does something in its generic made-up reaction style and produces B plus C. So maybe it's some sort of decomposition. And we then know that, or we predict that B is what subsequently reacts with D to produce E. This will then give us the overall equation because the B will essentially cancel itself out in the equation, leaving us with an overall reaction of A plus D producing C plus E. So we have what is potentially a two-step reaction pathway. But what we don't know from our theoretical hypothesis is which of these two steps are the slowest steps of the two, and subsequently which will be the faster of those two. This is where the rate equation comes in. The rate equation and the orders of reaction directly correspond to the number of molecules involved in the slowest step of the reaction. In this rate equation, it is telling us that one molecule of A is involved in the slowest rate determining step, which means because A is only involved in the first step, we know that this must be the slowest step and subsequently becomes the rate determining one. This is giving us a direct insight into the mechanism of the reaction and how these two processes occur. That means that the second step, once B has been produced, is fairly rapid compared to the first one. The speed of this reaction is defined by how quickly A can produce B and C. C is the product of the reaction, but subsequently B, in its then reaction with D, whatever that reaction may be, is relatively fast. But the rate equation allows us to evaluate that the rate determining step is the slowest one, and in our made-up reaction here, the step one reaction of A is the rate determining one. It doesn't, as we say, it doesn't necessarily mean that D wasn't involved in the equation, but because it didn't involve itself in the rate equation, we know it wasn't involved in the slowest step of that reaction. D is involved in the reaction, as we know, because it's in the overall equation, but as we keep saying, it's not involved in the slowest one. The rate equation gives us, as we say, an insight into the mechanism of the reaction, revealing the molecularity of the rate determining step. You will see various questions turning up, but as I say, once you've derived the rate equation, you can then have a best guess as to the experimental methodology of the reaction pathway. I hope that's given an insight into the kinetics through this series of clips, and thank you very much and good luck.